My name is Daelman. I'm the domain expert for the ground state calculations. And in this part, I will be not delving too much into the DFT, but rather in the precision surrounding ab initio calculations. And while this is mostly geared towards ground state, up to a certain height, it is also extendable towards excited state methods. So we're really going to be focusing on this newly added section called precision. After that, you've had this grand tour from Jose around NOMAD. Just for the astute of you, the version that I'm showing here is not this beta version. It's actually a developers only version that is used for the reprocessing that Jose briefly mentioned. You can notice this because before this was empty, but here you can actually find some statistics. So what is happening is when you reach out to us for a new feature and we implemented it, this feature then immediately becomes available to the developers and will eventually be updated on the beta version first. However, it does not automatically retroactively go to all the updates and start reapplying this extraction. So this is a very involved task that is done periodically to update the entire database. And right now we're going through this in part because of this tutorial here, just so we could kind of show you some nice statistics and some real case examples, not just something fully prepared. So currently, if you go to the beta version, this will still be empty, but once this reprocessing is done, this will be updated. But please feel free already to upload your GW or your BSE calculations. They should already be captured. You can already start helping out with the statistics there. Okay, with that out of the way, let's go into this precision menu. So let me explain what I exactly mean with precision. I'm mostly talking here about the convergence of the electronic structure and the parameters that can control this. The first type of parameters that come to mind here is the basis set, which you can basically ramp up all the way to the basis set limit. But there are also some integration grids that are used within the codes themselves. Typically, I wouldn't suggest this filter to be the first one where you start out with, right? Because convergence only really makes sense when you're comparing the same kind of system. Technically, even when you start modifying the geometry, you wouldn't, let's say, you're not sure if it will always converge to the same thing, right? So you would have to do another convergence run or something for the electronic structure. So a more typical approach to go about it is that you would first select the material that you want to use. Let's just take a very scholastic example, actinium. Let's take really only pure actinium, so the metal. Then you can maybe specify some types of properties if you know that you're interested in density of states or some kind of vibrations. In this case, I'll want to tackle all those that come from a flow. You can basically sort these menus to meet your needs. Let's also further specify, well, AFlow typically runs PBE calculations, but so you can further specify the methodology that you will use, be it GW or BSE or whatever is applicable to you. And once you have all of this defined, then you go back to the precision. And now, for example, if you go down, so you will see that the filter set automatically updated. And in this case, because this is running fast, you basically have a plane wave cutoff. And you can see that there are two groups here. Maybe you say, well, I don't really like the data that's coming out of here. I really am only interested in taking properties that are higher convergence, and then you just select, right? So that is the proper way to think of these filters. It's really the cherry on top of your filter pie, so to speak. Let's clean this menu out and go back to the top again. So I'll explain a bit of the layout here. So it is set up in such a way that we start off with very general quantities that hold true for about every material that you can that you will typically encounter here. Then also some quick filters, and then we come down to these basis sets. I think this is very self-explanatory. These are basically some categories that that specify with the type that you're dealing with. Typically, code will support one or a handful of these basis sets. So this is very much tied to the code, which you can specify here in the method section. I think they're all self-explanatory. Gaussian and plane waves actually refers to CP2K. I'll briefly touch on that later on. Support functions is kind of an additional category that we have, which fits everything that doesn't really fit in the rest, but I would say it mostly covers stuff like wavelets. So underneath the choice of the specific basis set, you then have actual properties that are basis set specific. And just to really convince you that this is true, let me just use this dropout option here. This is also one of our new GUI features. So what is really nice is that I can basically create a dashboard on the fly and use that. Let me drag that down here. So what you will see, for example, is that if I select plane waves, I will really be restricted to plane wave cutoff because it only makes sense there. APW cutoff is for LAPW or with local orbitals, and vice versa. If I were to select something here, you will see that this goes further down. You see that this is fully filtered down. Okay. So really, these quantities end up being further specifications of a basis set that you can find in here. So typically, it's good that you kind of constrain it if you have a certain basis set in mind, and then you can further specify it as I showed now. Let's get back to this overview. What I will do now is I'll go a bit more into depth in a couple of these quantities. I can imagine that at first glance, they seem pretty self-explanatory, especially if you're familiar with some of these basis sets. But I've seen that our audience is quite diverse in backgrounds. It's also that in NOMAD, what happens is that we really are accepting any type of workflow or way of generating data as long as it is complete, right? We try and facilitate that and put it into a standardized format. But we do not dictate how people work. You're free to come with your data, how you have produced it. But this means that within that diversity, the world is a very big place. There are always oddities and edge cases. So there is a lot of thought that has to go into even these seemingly innocuous types of quantities. And I'll actually get into that a bit. Let me just switch up. So as mentioned by Chema, we have this guide here with notes that you can go through at your own pace. Most of it I will be covering here, but I will be especially switching back and forth because I want to use some of the visual material here. So first I will explain this K-line density that you were seeing over there as a histogram. So basically what is happening is that when we try and model a material, most cases, we assume the material to be crystalline in nature, meaning that it is periodically being extended up to theoretical infinity, right, along several axes. We know from Bloch's theorem that we can capture the representation or the interaction between the unit cell and its images, be it that the wave functions are destructive or constructively interfering. We can represent that in reciprocal space using basically some kind of plane wave, basically Fourier basis set. This is then what we typically call the reciprocal space, so this K space. And along each direction, we will have also a matching here in blue reciprocal lattice. These do not necessarily have to line up with the axis in real space, but in the case of orthorhombic systems, they do. They don't even have to have necessarily the same length. That definitely does not hold in general. And then we basically sample all types of interactions, right? All types of periodicities using these different K points. This is due to the discrete nature of numerical codes. So this actually kind of takes me back to when I first started my PhD. Is one of the rules of thumb that they gave us is, well, basically you should make sure that this density always stays somewhere at around 30. So what they meant is we have these K-point samplings. We can basically see how many we are covering per unit lattice vector. And typically, you want them to be somewhat the same on all of the axes, meaning that suppose that I were to double my unit cell to create some kind of supercell, I would typically halve the K-space just to have the same type of representation. And while this in general will give you almost the same K density along each axis, what could happen is that here we are dealing with an integer, here we're dealing with a real number, so that due to the rounding, you get slightly different results. So while you can define a K density along each axis, just switching back for a second, here we are only showing you one number that is representative for the entire system, not for each axis, because they can be chosen a little bit arbitrarily. So what we really want for our users is that they feel sure that once they've specified the system of interest, method of interest, as I showed before, that then as they start dragging this lower threshold up, they are sure that they get calculations that have a better convergence, that you are really improving the convergence going from here to here, for example. Okay. So to make sure that that happens, what we do is we basically, when presented with these three axes, we only report the one with the lowest K density, the minimal one, as you can see here. NOMAD also extracts the dimensionality. Actually, this is a recently updated feature, and it can be found here. So we have this program that can recognize, regardless of whether your periodic boundary box is three-dimensional, whether or not the system that you've built is really three-dimensional, by looking at the geometry and if there's some kind of vacuum space in here in between, for example, in typical slab setups. At the moment, we cannot yet we only extract the K density for the bulk system, meaning that once you apply this filter, you're also filtering implicitly for bulk systems. However, we are working hard on adding this here. It's just that we have to properly extract them, the dimensionalities that still make sense, right? Because on this axis, you will get a very small unit lattice vector and then only one point or a very small number of points. So this can give some noise to that system. Another implicit aspect that comes from the idea of density is that typically we try and capture this in a single number. So this means that we have a equidistant fixed space sampling. This is not necessarily always the case. The first scenario that comes to mind would be band structures, in which case you're also implicitly filtering out for them already when looking for the K density. I think that's fine here because nobody in a real world setting would use a band structure to test for convergence. This would be rather something that you do at the end after you've already determined the level of precision that you want to work at to obtain a high quality property. So then we move on to, we move on to the cutoffs here. These are more basic set specific. I'm just going to jump over this code specific tier for a moment, but I promise that we will get back to that by the end. So let me see if this time I go back to the right tab. Yes. So I guess that in general, plane wave cutoffs are a little bit, or the plane wave basis set is a little bit more well known, but I'll just run over it very quickly. So similar to the reciprocal space that we're working in, what in the plane wave basis set, you basically try and emulate the same basis set, but internally inside of the unit cell. This is typically differentiated by noting this K and G vector, but they're both in reciprocal space. There are several parameters at play here, but the most important one is really the maximum K-wave factor that we sample up to, similar to with Fourier transforms, that as you go higher and higher in frequency, you can basically capture more detailed aspects of the function that you want to extract. So we could basically just extract the length of this vector and call it a day, but here at NOMAD, we really try to make these quantities as intuitive as possible, and this means also following community conventions when they arise. And one such convention is that you typically don't just mention the lattice length, but rather you convert it to its to what will be the maximum kinetic energy of such an individual basis set function when converted, and then basically we represent it on an energy scale. I'm kind of stressing this last point that we are working energy units to contrast it here with the APW approach. So in APW, there is one is operating with a muffin tin potential and really separating the space. So you will have these muffin tins that have their own type of internal description, and then you have this interstitial zone that typically is where typically the potential surface is very flat or has a very low curvature, and this is what is described using plane waves. So contrary to here, where the plane waves describe the entire space, here they are only describing this part shaded here in blue. But apart from that, they are described using exactly the same parameters. So one could, again, try and use this energy cutoff. It would technically make sense. But within the community, there is a different type of convention where what we really want to do is kind of have a reference of how well these plane waves are described in this interstitial region as compared to how much they could capture if applied to these muffin tin areas, right? So technically, as I ramp up, as I make my circle larger, I will get more and more nodes in my basis set. And the question is really how many of these nodes would fit into such an individual muffin tin sphere. And to kind of get a quick idea or a quick feeling of how these two properties relate to each other, the fact that you've now carved up your space, this is the standard definition. This is real space units with reciprocal space units, so that means that that you end up with a unitless quantity, right? So this might be very peculiar for somebody coming from plane waves, which is also, let's say, my main background. Moving into APW, that suddenly you use these units that you're so used to. On the NOMAD side, we try and already capture that. So I know there's a lot of information, visual information here in the GUI, but it is mentioned here in the form of the unit that you can find here and not here. These units, by the way, you can basically adapt them or set them to your needs via this icon here. And you can also hover over the quantities to get their definition, which is a bit more in depth, and it explicitly mentions that one is energy and the other one is basically unitless. So just to tell you that really all of these minutiae are being captured when setting up these parameters. So at this point, what I would like to do is delve. So Up to now, I've kind of shown you a couple of these features, but there's much, much more data that we extract from each calculation. It's just that either it's so specific to a certain scenario or it is so verbose that it does not make sense to place it here within these filters. But I'll show you how you can actually access them anyhow. Let me, in this case, maybe switch on tabs. So essentially, it is living here under. Okay, it's not picking it up. That's fine. So now I've switched to an overview card of an exciting calculation. And we can go back to this data here. So as Jose mentioned before, you can find these filters living under results. You go through to method, simulation, and here then you have this precision section with the quantities that I was mentioning before. But really for a more verbose or the complete set of computational quantities, you should look under run. Method determines the setup of run. There's no simulation here because it's only calculations. And now we have this new section called electrons representation. So electrons representation contains all the information or of the mathematical description of the electronic structure. So there are two quantities here of note. So one basically explains the basis set as a whole. And the other one explains where this is being applied to in the code. What do I mean by that? Even when you set your basis set values for a specific calculation, it doesn't mean that for every task internally in the code, those settings will be used as such. For example, the level of detail or precision by which you want to describe a wave function might differ from an electron density because this is now a composed value and it has different convergences. It might even differ when you then put this electron density inside of an exchange correlation functional. So depending on the task at hand, you will get different settings. This doesn't have to be just basis sets. It can also be additional grids, integration grids, or augmentation grids, such as used in VASP. What is important to note is that the values that I'm showing to you in entries, they all come from wave function. So we make sure that we are really comparing the same property here and its description when showing that to you. So then we have here this basis set. Most basis sets are not really one big monolith, but they can be understood to consist out of several parts that each have their own individual parameters. I mentioned this APW, and it's really an APW family where we have this interstitial region captured by plane waves. You can see again this cutoff fractional, and then we have these muffin tin spheres. Right. Here, I would probably want to, for a moment, go back to the notes and give a very brief overview of what the APW basis set actually means. Okay, so I don't want to turn this into some kind of lecture on APW. I've actually seen that there are bigger experts in the audience than myself. But I just want to give a very quick recap so you kind of get a flavor of what is going on. So essentially in APW, so what are you seeing here? We're seeing here at the origin, basically, there is an atom nucleus, and we're looking at it from the radius out, seeing that our space is being divided between the interstitial region described by the plane waves, and then also the muffin tin sphere. Typically, within the muffin tin sphere, you can kind of distinguish between the core electrons and the valence electrons. For the case of the core electrons, because the muffin tin is spherically symmetric, you actually obtain the Dirac equation for a multi-electronic atom, which is pretty standard fare to solve. So this is not the most complex part. However, and on the valence side, you have to match with the plane waves outside. So you have some kind of coupling there, which prohibits you from simplifying it to that specific case. You can still use the spherical symmetry to your advantage and basically develop a basis set based on spherical harmonics, such as Bessel functions or the likes, which are then have weights of themselves that are defined for the radially varying, as you can see here, but they also are dependent on this energy parameter. This energy parameter is the Hamiltonian eigenvalue that you will get back when solving for the Schrödinger or a relativistic Schrödinger equation. So basically, it is the specific orbital energy. But this seems a little bit paradoxical if you try and approach this directly, because essentially what it means is that you're trying to solve for a quantity using a basis set that is defined in terms of the quantity. This is manageable. What you can do is basically try and optimize this quantity itself. So that's what you see in the pink here, is what you would kind of get as an effect as you start playing around with the energy parameter. But this gives you a set of nonlinear equations, and it's, let's say, pretty resource consuming to have this type of approach. This is the original APW formulation as specified by Slater. However, more modern codes, what they will do is they will try and linearize or cast this nonlinear problem back into a more easy linearized version. In which case, it's actually, there's a very simple workaround. You simply fix this energy parameter. You only allow it to change depending on the spherical harmonic parameter L, and also to change by Muffington to Muffington. But apart from that, it is fully fixed. It no longer varies. This, of course, even though you can have some good guesstimates of what would be close to the actual physical value, the problem is that you will it's very hard to account for all of the physics, such as dispersion and other types of interaction, bonding, anti-bonding. And typically you will have some kind of discrepancy between the actual final result that you would have gotten using this basically perfect approach and then using your approximation. So the workaround here, and this is, by the way, what typically most codes in most modern codes in practice call an APW orbital. The workaround here is that you further extend or further enhance that orbital. One option is, and this is again somewhat similar to when you're working with for example, sinusoidal basis set. Just think of a second order differential equation where you get basically a two-dimensional basis set. One is the sine, and then you have the cosine, and by varying them, you can also change basically the position of the peaks. So this is somewhat of a similar idea, basically using higher order derivatives with respect to the energy parameter. You can keep on increasing the correction here. So if you have only the first order, this is called a linearized APW. Another alternative solution would be to take the same kind of formulation, maybe with higher orders, and cast it into a local orbital. The main difference here are the boundary conditions. So as mentioned before, they have to align with what is happening on this plane wave side. But essentially, so you have to make sure that it's continuous. And then if you go to higher orders, the continuity will explain itself as being smooth and so on and so forth. But here, as the name suggests, it is relocalized within the muffin tin. So it's fully zero outside, and it has some proper, well-defined norm internally. And the nice part with these LOs, these local orbitals, is that you can kind of add them anywhere to any type of orbital. This doesn't just have to be APW that you further extend. Other types of cases include semi-core states, which essentially are technically core states. They shouldn't belong to the valence, but they are kind of leaking outside of the core, and basically you would prefer to treat them as if they were actual valence orbitals. So then you can just add a local orbital there, and that takes care of that, or several. You can actually compound them. You just have to attune this energy parameter to be in the right region. You can also just bump up this energy parameter to describe the unoccupied orbitals, which become very important at the beyond DFT methodologies. The big takeaway here, I'm seeing that I'll just speed up a little bit. How are we still doing with the program, with the time? Should I run a bit, or is it still fine?
I think you have still 10 minutes or so.
Okay, that's plenty. That's fine. I can finish in that. So I know this is a lot of information to ingest, especially for those of you not familiar with APW, but the main takeaway that I want you to get here is that this is a very versatile, very flexible and customizable basis set, which makes it great for running calculations because you can customize to whichever problem that you encounter, but it makes it also very complex to kind of try and capture that into a standardized framework. This actually differs from code to code. So rather than trying to come up with some kind of convoluted scheme here, we thought that it would be more, let me see here, it would be basically clearer to simply unroll all of these orbitals. So we will go here in this orbital section over all of the valence orbitals in order of increasing L channel, and also increasing order. And as you can see, for example, what then happens here is that you get, for example, in this case, you see that the person started out in the lowest L channels. So these are the ones that would most closely describe the S and the P orbitals. They start out with the APW with LO corrections. You can have these LO corrections also for different reasons if they are aligned to different energy parameters. And then from the higher order harmonics onwards, it becomes LAPW. And you can fully customize this, which we all try and capture and fully unroll it, being very verbose. Of course, this makes it a little bit complex to compare between two cases if you're working with the same tin. In that case, I would suggest that, as Chema showed before, you can basically download this data. It's very simple in Python to just hash it, and then you have a simple comparison feature to see if you're really working with the same setup. I should also maybe mention that this was a case for silicon carbide that I was showing, so we also explain which atom type is being explained, which is being addressed in which side. This is actually a reference to this atom parameters section. So atom parameters captures all of the methodological definitions of basically atom types within your calculations, so the way that you're simulating them. This makes that by times it has some overlap with electrons representation, but whenever this occurs, we will make sure that they basically cross-reference. The most important thing is that you can find the data the way that you want to look at it. So as long as you understand more or less in large terms what electrons representation or atom parameters mean, you should be able to find something that makes sense under that. So we try and give you some kind of semantic findability there. Atom parameters also houses pseudo-potentials. It's exactly the same case. I think I'll step over that example for now, just because of time reasons. I'll move to one last example. So that is here in the precision. As I promised, I would end on this code-specific tier. I have another example prepared for that to kind of introduce it. This comes from FHI aims. Let's go back to the data section. It's quite verbose, so let's see if it can load it on time. In the meantime, are there any questions already or any comments? If not, you can briefly, you can already start thinking. I'll wrap up and then we go to the questions or to a break, a much deserved break. So in FHI aims, if you go again under run method, as Jose mentioned before, we have this, we have some hidden quantities as well that you can show, that you can make visible. One of these are these code-specific quantities. So typically when you find something like this, there are one of two cases. Either this has not yet been standardized or it doesn't make sense to standardize because it has no real comparison among similar codes. In this case of FHI aims, it's very much the former. We've now added a lot of features for plane waves and APW in particular, but the next one that we will be tackling are atomic orbitals, atom-centered orbitals. So for the time being, you will find this here, but later on it will migrate towards electrons representation. Here you have this section defining the FHI aims basis set. These are some global parameters, and then you have specific ones for each element, and you can see really how verbose and how many of these parameters there are. Now, just imagine that you're a student, a PhD student, just starting, very fresh, and they ask you, hey, run the system in FHI aims. I mean, even for an expert, it would be very tough to try and define all of these settings, right? So what happens is that several codes, they have their own set of suggested parameter settings to help you get started. And also to kind of compare, to basically compare across the user bases with similar types of settings. These are typically derived from benchmarks, as is the case also with FHI aims. In this case, it's typically some kind of list that you can access via their GitHub, and you can just copy over these parameters. And there are several categories with different amounts of precision, because the code developers realize that depending on the task at hand, you don't always need the highest precision. Sometimes you want to go for something that is less resource consuming, or first pre-converge something and then later on go to a higher precision. This type of hierarchical categories is what we refer to in NOMAD as tiers, right? So they're really precision tiers. And they basically manage to summarize all of this complexity that you see here in a single term. Isn't that truly wonderful that you can capture all of this complexity and hide it behind that individual term? And that is basically what we make searchable in this part over here. Now, this is still very much tied to the code. Each code has its own internal settings, and even when they have similar basis set parameters, they most likely will have different grids. We are definitely interested in extending eventually these grids beyond specific codes towards at least the same basis set, where it makes sense because you're somewhat dealing with the same parameters. That initiative was actually kicked off end of last year with a survey that we sent around to several code developers. And we got a lot of feedback there, and a lot of responses, part of which actually informed these properties that have been implemented now. And we will definitely be further following up with that and reaching out again in the near future, trying to move beyond these code-specific tiers. But for the time being, I think this is a very good intermediate and a very good jumping off point. Because they are tied to codes, they have to be formulated first by writing out the code name. You can see this here with this suggested example, then a hyphen, and then you basically specify the tier name. This is case sensitive, but as you start typing, you will basically get some suggestions anyhow. So don't worry too much about that. Overall, this is a very nice filter that can save you a lot of hassle trying to play with these quantities and then even capture all the other quantities that are not made available in filters. So it's definitely something that you can try out so once you come down in the specification down to the precision level, you can start specifying this here. However, there is a caveat here. This is also very greedy, a bit of an overzealous filter. What I mean is that basically what we do is we match up the parameter settings with the specific tier. But what would happen, let's say now that you use these parameter settings that I showed you before, I think those compared to the tight tier in FHI aims, and you say, okay, I don't want to go to really tight, but I do want to tighten it a little bit. So I'll just change this single parameter because this is the one that makes most sense. Well, in that case, I guess we could still kind of have an idea of, okay, you either tightened it more or less, so the precision changed more or less. But the problem is, what if you start varying two parameters at once in opposite directions? Now it's a question of which one trumps which one. How do they relate to each other? This is a very complex question, even for, I think, for the code developers themselves to ask. That requires a lot of benchmarking. So at the moment, we rather give you something that is a little bit more restrictive, but works very, very well, rather than immediately promising you the moon. But definitely these features will keep on being further developed. And hopefully at some point we can capture this type of complexity. For the time being, this means that you really will only get calculations that specifically match up with the tier. This means that you might be leaving out a lot of calculations that could be interesting for you. So definitely try this out just to get a quick flavor. But then if you see that your data set you're getting back is a little bit too restrictive, maybe consider doing it the more manual way. So with that, I've come to the end of my part. Any questions? I understand that it's a lot to take in.
So maybe, Nathan, you can comment on how long do the user have to wait before they can see what you are showing today? Because I mean, if you go to the staging, to the beta version, you can see these let's say quantities, but essentially nothing is populated.
Yes. So again, this depends mostly on the reprocessing. It's the head engineer Marcus who's in charge of that. I would say at the rate that we're going, I would say a month or two max, given that it is summer and people tend to go on holiday. So rather spend your time at the beach rather than behind here, but behind the computer screen. But once this reprocessing is complete, it will be updated also on the main page. I'd really have to refer for an exact timeline to Marcus. Yes, the exact metrics. Maybe Jose has some idea there, but I think a month or two would be a very safe bet.
So this is for the old data, right? So the data that have been uploaded in the past, while the new uploads will be automatically be processed with the new features, right?
Exactly. So even for your own data
in the
set,
beta version.
Yeah. Yes, yes, they've already been added. The beta version tends to get updated much more quickly. So if I just go back a second, suppose that you were
I knew the answer. I was just advertising.
Yeah. I know. So actually, you can already use this to then kind of investigate your own data set, right? I didn't show this right now, but essentially you can start composing a scatter plot. And then basically compare a certain quantity that's being extracted compared to the convergence, right? You just narrow it down to your own data set, and you immediately get some nice figures that will inform you on how you're doing with the convergence. This kind of runs into an alternative way of using NOMAD, especially local installations called NOMAD Oases, where you can also use it for data management and real-time course corrections to your projects and the data that you're generating. So basically, you then have analysis more tightly coupled to the data production.